Okay. Hello, everyone. I'm Gaole from the Ming University of China. In this talk, I will introduce our paper about knowledge graph completion with user item interaction data. First, let's look at the background and motivation of this paper. Knowledge graph is typically a multi-relational entity graph containing entities as nodes and relations as edges. Knowledge graphs are important resource for many artificial intelligence tasks, but often suffer from incompleteness. To address this problem, researchers propose a task knowledge graph completion. Knowledge graph completion aims to automatically infer the missing fact information in knowledge graph. For example, predicting a missing entity. Just like the picture show, if we don't know which genre Taylor Swift belongs to, we may try to complete the query triple Taylor Swift genre question mark to find the answer of the triple. Knowledge graphs are often utilized in application systems as our observation. Many knowledge graph entities correspond to online items in application systems. For example, Taylor Swift's song Lover can be found in both Freebase and Last.fm platform. For knowledge graph entities aligned to online items, we can obtain fact triples from the knowledge graph as well as rich user item interaction data from the application platforms. To our motivation, user item interaction data has explicitly reflected users' preference at the item level, while it is likely to contain implicit evidence about entity semantics, which is potentially useful to our task. Have a look at this example. In the figure, the users Steve and Bob like the songs from both singers, Taylor Swift and Broad Paisley, due to their similar style. Such co-occurrence patterns in user item interaction data are helpful to infer whether the two singers share the same artist genre in knowledge graph. Here we define our task. Our task is given a query triple HR question mark or question mark RT. We aim to predict the missing entity given both the knowledge graph information and user item interaction data. Indeed, several recent efforts have attempted to leverage both knowledge graph data and user item interaction data for jointly improving the knowledge graph completion task and related recommendation tasks, such as path-based methods proposed by Sun et al. And regularization-based methods proposed by Peel et al. And graph neural network-based methods proposed by Wang et al. These studies mainly focus on developing data fusion models for integrating the two kinds of data source. Example, learning representations in the same space or sharing the same information representation across different resources. However, the two kinds of data sources have very different intrinsic characteristics, and it is likely to hurt the original representation performance using simple fusion strategy. In addition, user item interaction data is usually very noisy since user behaviors will be affected by external events or other influencing factors. It may be problematic to directly incorporate the knowledge information for inferring knowledge graph facts. To solve our task, we have to consider the effects of data heterogeneity and semantic complexity on model design. Considering the overlap between knowledge graph entities and online systems, we introduce an extended entity graph to unify the knowledge graph information and user item interaction data. The extended knowledge graph consists of a union set of knowledge graph triples and user item interaction triples. Since our task is to leverage user item interaction data for learning useful evidence to the knowledge graph completion task, we organize the entity graph in a user-oriented layer-wise structure Specifically, user nodes are placed on the first layer. Then, the aligned entities which correspond to online items are placed on the second layer. The other, the other nodes are organized in layers according to their distance. We call this graph interaction augmented knowledge graph. Then we will introduce the challenge in this task and how we address it. The major challenge can be summarized as how to learn useful knowledge graph information from user item interaction data for improving knowledge graph completion task. To address the first challenge, we develop a two-stage representation learning algorithm based on graph neural networks. The second challenge is how to integrate or utilize the learning information in knowledge graph completion methods. To address the second challenge, our idea is to develop a specific evaluation component that incorporates and learns user preference information about entities for evaluating a candidate entity given a query. Meanwhile, we keep a prediction component to produce the candidate entity without using user preference information. By mapping the two components to discriminator and generator respectively, our idea naturally fits into the successful framework of generative adversarial networks. Let's zoom into how two-stage representation learning work. If we want to model preference information for entity E in knowledge graph, we should first find related users and learn entity-oriented user preference for them according to the graph structure. And then we collect user preference from the related users. In the first stage, we perform the information propagation from knowledge graph entities to users. The update strategy is a combination between the original embedding and the received embeddings from forward triples. Look, we propagate information from entities in layer 3 to layer 2, layer 1, and finally, we obtain entity-oriented user preference for users U1 and U2 in layer 0. In the second stage, we adopt layer-wise graph attention network to collect user preference with regard to high-order connectivity. The representation of user nodes are learned from the first stage, and we obtain preference representations for entities in layer 1 and then target entity in layer 2. It can be proved that the collected preference representation is indeed a linear combination of user preference representation. Considering data heterogeneity and semantic complexity, we design an adversarial learning approach to utilizing useful information from user item interaction data for the knowledge graph completion task. Our focus is to train a capable discriminator that is able to leverage knowledge graph information for the knowledge graph completion task. And the role of the generator is to improve the discriminator and help the fusion of user interaction data. In this way, we can fully utilize useful evidence from user interaction data in the discriminator, and meanwhile, avoid direct influence of user interaction data on the knowledge graph semantic space modeled by the generator. Let's look at the details of the discriminator and the generator. Our discriminator D evaluates whether the entity T can be the answer to a given query HR ? By computing the following probability. In the formulation, VH and VR are known parameters for knowledge graph entities and knowledge graph relations. Besides the known semantics representation VH, we enhance the entity representation using the entity level preference of the users with high order connectivity. Then we look at the generator. For each query, HR question mark, the probability distribution to sample a candidate entity from candidate entity set is defined as following formula. We can implement the query representation as any way as we needed. Here, we just use the hard-mode product to or target entity embedding and relation embedding as query representation. After that, we concatenate the query representation with a noise Z, which is drawn from Gaussian distribution with zero mean and covariance. And then use a vector to score all candidates entities and form a probability distribution with softmax. For the discriminator, we minimize the foreignness of the real answer and the NG fake samples from the generator. For the generator, we first sample NG fake samples from candidate pool and then train it with policy gradients. For more training details, please refer to our paper. Then we will move to the experiment part. Our datasets are organized with item entity alignment. These alignments are obtained from KB-Freak datasets, which will be introduced then. Our dataset covers 3 domains: movie, music, and book. We split the knowledge graph dataset with 8:1:1 ratio. For more detailed constructions, please refer to our paper. KB-Freak is a dataset for linking knowledge base with recommender systems. It organizes the item entity alignments by linked ID pairs, which consists of a recommender system item ID and a knowledge base entity ID. Here is an example about item entity alignment from film Spider-Man and Spider-Man 2 to Freebase entities. Once we have the item entity alignment, we can obtain rich relational facts from knowledge base with entity ID. KB-Freak provides a large amount of linkage, and we can obtain rich relational facts with these linked entities. Now, one-hop Freebase subgraph of each domain has been released, which provide rich relational facts about linked items. You can also follow our code to obtain subgraph of 2 and more hops. You may have a look at this dataset, which is useful for both knowledge graph and user item interaction topic. For evaluation, we follow standard knowledge graph completion evaluation with filtering setting. For each test triple HRT in a dataset, 2 queries, HR question mark and question mark RT were issued. We adopt mean rank, top K hit ratio, and MRR as our metric. Our baselines have a comprehensive coverage of the related models. To summarize, we categorize the baselines into several groups shown in this table, according to the technical approach and utilization of user interaction data. First, translation-based methods, which model triples as relational translation from subject entity to object entity, such as trans-E, K2P, and co-FM. Second, semantic-based methods, which model query and answer entity with neural networks, such as convolution neural network, and then match them in semantic space, such as DSmart, conv, and conv-trans-E. Third, graph neural network-based methods, which model data sources with graph neural networks, such as RGCM and KGAT. And final, GAN-based methods, which are trained with GAN framework, such as KP-GAN and our approach UP-GAN. Main results on 3 datasets are shown in this table. Overall, Smart and Trans-E are the best baseline methods. KBGAN substantially improves over Trans-E on all datasets, which indicates the usefulness of adversarial learning. Our approach, UPGAN, is consistently better than these baselines by a large margin. Then let's look at other methods which incorporate user-atom interaction data. Overall, the three methods that jointly utilize large graph data and user-atom interaction data seem to give slightly better results than Trans-E. Among them, KJT achieves a better performance on book dataset than the other two datasets. To effectively utilize the user-atom interaction data, our approach has made several technical extensions. To examine how each of them affects the final performance, we conduct ablation analysis. There are three variants about our approach. The first one is the approach with only discriminator component. The second one, the variant replaces the two-stage representation learning with a graph neural network architecture similar to RGCM. And the third one, the variant drops the enhanced entity representations. These results indicate that the proposed techniques are useful to improve the performance, especially user-atom interaction data with a suitable modeling way is more important for our approach. For the sake of time, please refer to our paper for other detailed experiments. Here, we come to a case study of the noisy case. This example shows we try to find the literacy rise of the rift wall cycle. Starting from the target entity, the rift wall cycle, we can identify 128 related users in total with the breadth first search extension based on the interaction augmented large graph. Given two candidate literacy rise, Serpent War Saga and the Wheel of Time, a straightforward method is to count the number of literacy rise that has been read by the related users. However, the Wheel of Time is much more popular than the correct entity Serpentwa Saga. It has 13 users in common, but the right answer just have 17 common users. It indicates that simply using the user interaction data may incorporate noise. As a comparison, by running our approach, we can identify more important users on the graph. As we can see, the two users with ID 770C0 and 7VLI5 are assigned with very large attention weights by our algorithm. An interesting observation is that legends of the Rift War and Serpent War Saga can be associated with the two selected users. Based on the known fact that legends of the Rift War belong to the Rift War cycle, our approach is capable of identifying Serpent War Saga as the final answer. In conclusion, in this work, we propose an effective learning approach for learning useful information from user-atom interaction data to improve large graph completion tasks. In the future, we will investigate into how our models perform in other domains. Our code is open sourced on the GitHub. You can also find the atom entity alignment from KBFreak project. Thanks for your time and listening.
Thank you so much for this great talk. Questions, anyone? Okay, so I have some questions, if it's okay. I ask whether, I would like to know whether you tested generator with different noise methods or you tried just that one.
Do you mean try different formulation of the generator.
So you applied some noise.
Yeah.
Yes. Why did you pick this specific noise function? Did you check others?
In our opinion, the general adversarial learning are usually applied in computer vision. They often adopt noise to enhance they often adopt noise to combine to learn the distribution. We just concat the query and the noise to form to add more randomness.
Okay.
In our experiment, we just try to use generator like this format. We may have further research, just as you say, to more format or generator.
Okay, thank you.
Thank you.
Any other question? Okay, so I would like to thank the author, presenter. We are a bit ahead of schedule, so the next presentation should be in 10.